Hi everyone, this is Mudhawat Ravi. I am pursuing Bachelor of Technology in Mineral and Metallurgical Engineering, BTech final year um, from Iitian Dhanbad. So today I have chosen the topic from the physics, that is mechanical properties of solids. In that I have chosen these following introduction topics, and as well as I will go deeper into it as we move forward. So first, to determine a material or solid material, we have to see its properties like malleability, ductility, sonority, and brittleness of the brittleness is not a property, by the way. So these are the properties we have to see. In that, first. To see its mechanical property of a solid, first we have to see what is stress. Stress of a material is force restored in the body. Stress is force acted on a solid body per unit cross-sectional area. Like stress is denoted by this symbol, and that is force per unit area, cross-sectional area. This is how we will formulate the stress. And other is strain. That is, strain is change in dimension by the original dimension. For example, if you apply a force on a body or any external force on a body, it will deform for sure. If it deforms, it will have some dimensions initially, and after deforming it will have some changes in its dimension. So we will calculate strain in the function of it, like change in the dimension by the original dimension. For example, if the body's length is changed, then the change in length divided by original length. If the body's diameter is changed, change in diameter by original diameter, like that. And next is Hooke's law. Hooke's law, in that what is the significance of Hooke's law is, in this, stress and strain are both related by the Hooke's law. Like Hooke's law is actually stress by strain. This is symbol of strain. So Hooke's law is valid till the elastic limit of a material. For that, you have to know elastic limit. Elastic limit is if a body is deformed to its to some extent, if it regains its original dimension until that point, until that force, until that stress or strain, that is elastic limit. If we cross that, if we cross that stress or strain, the body will not regain its original dimension. So until that limit, elastic limit is called. Until that is Hooke's law holds for this equation. And from that, elasticity. In that elasticity is a material. It's a previously I explained about elastic mean, no? Elasticity of a material, like if a material is acted or some external force has imposed on it, and it has changed its dimension for some extent of time, for instance, and after removing the external force, and it will came into its original dimension and its shape, then it is the material has elasticity. And other is plastic deformation. Plastic deformation, as I said earlier, elastic limit. If you cross the elastic limit, the material will, if we more further increase the force or external pressure or force we will apply on a material, then it will not regain it into its original position. It will stay as so plastic deformation of a material is after applying more force than the elastic limit, like more applying more stress or more strain on a material than its elastic limit, then it will go to plastic deformation. if once a material is went into a region of plastic deformation, it will not gain its original dimension. It will be plastically deformed. Its restoration energy inside the material will be not capable to hold it into its original dimension. So the material will become ductility. And Young's modulus is the proportionality constant between the stress and strain. Until a elastic limit, stress is directly proportional to strain. For the for this elastic this proportionality constant, we will add a proportionality constant, that is Young's modulus. Young's modulus is denoted by this symbol. So we will write this expression as stress is equals to this thing. The next modulus is stress by strain, and this is how this Young's modulus is. It is a modulus. So many types of modulus are there: rigidity modulus and bulk modulus, and further so many there. So after that, I will explain this necking and fracture through a diagram. So until this is, I think it is everyone is satisfied. So I will draw a graph between the stress and strain. So until this point, the material has elastic limit. Like until this value on this x-axis, which is denoted as the strain, until this value of strain, the material's dimension will be it will gain its original dimension. It will not go into plastic deformation, and it's a maximum stress value for the elastic limit of a material. And this is upper yield point, and this is lower yield point, and this point is called, actually this is a maximum stress point. We cannot apply more force than this. This is a maximum stress we will apply on a material. And from here the material starts its necking, because if once a necking starts, even you apply more load, the material will not restore its energy, because it will, once it starts necking, its dimension, like the material is like this initially, and we are applying force laterally, then the material initially in this dimension, it will further went into like this. So here starts the necking of a material. This point results in fracture of a material, failure of a material. It depends on the material's composition and other its manufactured process. And if you further increase the strain of the material, then it leads to fracture of a material. Finally, the material will break. So further we have to see whether the materials promoted some mathematical models, like we know stress is equals to force per unit area, and strain is equal to change in dimension by, I am taking dimension as length is changed, only in length of material change. And further is we know Young's modulus is stress by strain, as I said earlier. And if we substitute this 1 and 2 into this third equation, we will get Young's modulus is equals to FL by A delta L. So this is Young's modulus. From this equation we will get F is equals to A Young's modulus A delta L by L. So this is a force which is act on a material till the elastic limit. To find the work done of the material, we can easily do work done is equals to force into change in length, the displacement, force into displacement. We can do it like we can apply this here, integrate it from 0 to L because it is its length, we are assuming length as L. So if we integrate it, we will get work done on that material is equals to x modulus A delta L by L into integration of that is L square by 2. So we will get work done is equals to length, fine, length and length will be cancelled, and half of YA delta L by that's it. See. So we can see square. So we can apply this. We know that force is equal to YA delta L by L. YA delta L by L. So we have this equities here. So we can substitute this force value in this equation. So we will get base of this we can substitute FL square. So for better clarification of the of all of these topics which I thought before. So first, for example, we will find if a material is hanged freely, then its elongation due to its own weights by including all of the factors. So we will take a rod which is hanged to a hinge which is freely elongated, and its length is L. Initially its length is L, and further after, because of its own weight, it has changed its length to delta L. So the total length will be L plus delta L. So to find out the change in length of a material of its own weight, let's assume its weight, its mass as m, mass m, and density is rho, force acting on it, normal force acting on it is F, and so on. So let's derive its change in its own length. So first we have to see, we know F is equals to so I've seen so many JE Advanced and JE Mains papers for making this 15 minutes video. In that I have found it's Poisson's ratio. About Poisson's ratio. Poisson's ratio is so Poisson's ratio. Poisson's ratio is a material is deformed in two dimensions, like lateral strain and longitudinal strain. So it is a ratio of lateral strain to the longitudinal strain. For example, I have taken a cylinder which is of radius r and length L. So to find out its Poisson's ratio, change in r. Initially, its radius is r. After applying some strain, lateral strain, we'll get delta r, some change in radius. So it is ratio. Initially, the material is like this. after applying its radial strain, its radius has changed from r to small r, and after applying its lateral strain, its length changed from L to delta small l. So for this change in two dimensions of a material, we can find out by the Poisson's ratio. Generally, it's negative because the material its change in length, like original length minus final length. Final length will be always greater because the material is changing. Poisson's ratio is to change in two dimensions of a material. Like if you change the radius and the length of a material, so we can let's see how it is changing. If its length initially its length is L1, and it's after elongation its length is L2, and initially its radius is R, and after radial strain its radius is decreased. So we have seen L2 is greater than L1 and R2 is less than R1. So the by solving it, Poisson's ratio is delta L lateral strain by longitudinal radius strain. So it will always be negative because its dimensions will change such a way that if we increase the length, its radius will be decreased. If we decrease the radius, its length will be increased, as we are seeing here as an example. So we always keep Poisson's ratio in negative sign. So generally the Poisson's ratio is ranges from 0 to 0.5. This is how we can learn more about mechanical properties of solid. Thank you, and for giving me this opportunity.